Edward Witten will tell us what we can hope to prove about three-dimensional Yang-Mills theory.
Thank you. So I have to say that after hearing this morning's talk, I thought I should have planned to talk on 2D Yang-Mills theory. Because while both of this morning's talks made me think that, one was that Arthur's talk made clear a lot of nice stuff that's been done, but also a lot of nice stuff that could be done if there was a renewed effort in two-dimensional Yang-Mills theory. But also, Witten was telling us about this problem that maybe will be solved with PDEs. But if it isn't solved with PDEs, maybe it should be solved with quantum Yang-Mills theory. But these thoughts came a little bit late. I had this talk already prepared about three-dimensional Yang-Mills, and it was a little bit hard for any correction. So we're going to proceed in 3 dimensions. Now, the title, What We Can Hope to Prove, perhaps should also include what we probably can't hope to prove. So the reason for giving the talk, in part, is that having a clear picture of what one can and can't hope to prove may help with strategies for proving what one can prove. Of course, implicit here is a belief that the study of quantum Yang-Mills should be reinvigorated. Personally, I think the relation between mathematics and physics will remain unsatisfactory unless the program of constructive field theory is reinvigorated in some form. But unfortunately, I'm not much more than a kibitzer here. So I thought the only way I could help would be to offer some musings about what one could or could not to prove if one were trying to prove things about three-dimensional Yang-Mills theory. Of course, as I said before, we could have had the lecture about 2 dimensions, but at this point, we're in 3 dimensions. Now, I'll concentrate on 3 dimensions because if the study of Yang-Mills theory is going to be reinvigorated, 3 dimensions will be an interesting target case. It's a lot harder than 2 dimensions, where a lot's known already, but as I just told you, also in 2 dimensions, there's an awfully lot more that should be done, and there's a lot more applications that the stuff that's been done ought to have that haven't been done yet. But anyway, 3 dimensions is much tougher than 2 dimensions, but 4 dimensions is a completely different order of magnitude, mainly because the renormalization program is much more complicated. Now, some of my views about 2 and 4 dimensions will become clear anyway as we go along, and I'll make a few remarks at the end. So here's the action of Yang-Mills theory, which I've written in 2 different ways, depending on which you like better. F mu nu is a 2 form, the curvature of the Yang-Mills connection A, and the action in Euclidean signature is essentially the square of the curvature, or we can write it like so using the Hodge star. And since we're in 3 dimensions, the parameter g squared has dimensions of 1 over length. So classically, it has dimensions of 1 over length. Classically, there's no equivalence between length and mass. But quantum mechanically, you've got h bar, and you can say that g squared has dimensions of mass. Or energy, since you also have the speed of light relativistically. Now, the classical action isn't scale invariant, meaning that if you take a positive real number lambda, and you rescale the coordinates of R3 by a constant lambda, the action is not invariant in 3 dimensions. But it's simply multiplied by a constant. And when you vary the action to get the classical equations of motion, you don't care about an overall constant. Actually, that's why we don't know about Planck's constant. It was set to 1, but it would have been in the denominator there. So the fact that the classical equations don't know about Planck's constant is more or less the fact that they don't care about the scaling. So the classical equations are scale invariant. They're invariant under rescaling of the x's by a constant. And more or less because of this, these equations describe nonlinear waves that travel at the speed of light. So relativity would allow you to have a wave that's the classical limit of a massive particle. It would mean a wave that has a certain minimum frequency of oscillation. But scale invariance doesn't allow you to have a minimum frequency of oscillation. So these are nonlinear waves that travel at the speed of light. Although the classical theory describes nonlinear massless waves, it's believed that quantum mechanically the theory has what's called a mass gap, which was an important figure in Arthur's lecture, actually. So the mass gap is a statement about the spectrum of the Hamiltonian which we will call H. A reasonable quantum field theory has a ground state, omega, that's annihilated by H. And saying that there's a gap, a mass gap, means that the ground state is in the discrete spectrum. It's separated by a gap from the next eigenvalue of H. So that the next eigenvalue, which is equal to what we call m, is strictly bigger than omega. Sorry, 0, which is the energy of omega. So this is, in the terminology of Arthur's lecture, the lower mass gap. The mass of the lightest particle above the vacuum is m. Arthur referred to an upper mass gap, which says that m is also in the discrete spectrum, and what's after m is higher still. But that more subtle property won't be important in this lecture. Now, apart from the statement about the spectrum, the gap is a statement about the behavior of correlation functions in Euclidean signature. So we consider two-point functions or correlation functions of operators normalized so that their one-point function, their expectation value in the vacuum, vanishes. So these are called connected two-point functions. Connected two-point functions decay exponentially at large distances if there's a mass gap. So that's an extremely useful property. It means that faraway regions of space are approximately decoupled from each other to within exponential errors. So the fact that space is infinite in extent is one of the problems in understanding quantum field theory rigorously. But when you have a mass gap, that problem is drastically reduced, because to within an exponential error, large but distinct regions are almost decoupled. So a mass gap, well, if it's true, it's one of the most important facts about a theory mathematically, but also physically, as I'll say in a second. So the existence of a mass gap is an experimental fact in four-dimensional Yangmill's theory, and it's strongly indicated by computer simulations in both 4 and 3 dimensions. In 4 dimensions, this is one of the most important facts about strong interactions. So the mass gap in strong interactions is not only not 0, but in everyday units it's pretty big. Well, 100 million times the energy scale of chemistry and atomic physics. So the energy to create a particle that requires this mass gap to create it is hard to come by in everyday life, which is why the strong interactions aren't more obvious in everyday life. That's why they only were discovered in 20th century laboratories. Apart from its importance in physics, from a mathematical point of view, the mass gap, well, I kind of said this already, it's a tremendous aid in understanding the infinite volume limit. So what I've written here is a variant of the way I explained it before. The mass gap means that the approach to infinite volume limit is exponentially fast, and this gives one some elbow room in making estimates. If you're trying to prove that an infinite volume limit exists, and in fact there's exponentially fast convergence to that limit, your estimates don't have to be nearly as precise as they would have to be if the approach to the limit is more delicate. Now, in physics, okay, again, I kind of said this already. In physics, the role of the mass gap is to hide quantum phenomena at long distances. So long distances are where we live because we're much bigger than atoms, for example. So we're discussing phenomena that are hidden at distances much less than the size of an atom. So, for example, electromagnetism is described by U1 gauge theory. There's no mass gap there, so electromagnetic phenomena are obvious in everyday life, and freshmen learn about them. Freshmen learned about electromagnetism and not SU3 gauge theory, and that's not only because SU3 gauge theory is non-abelian, so it's more complicated. It's also because SU3 gauge theory has a mass gap. So freshmen don't know about the phenomena it describes, because those are hidden at subatomic distances. So if a theory has a mass gap m, then at distances bigger than 1 over m, the effects of the theory are hidden. And that's why in everyday life we see electromagnetism and not strong interactions. Now, mathematically, to those who come from a math background rather than a physics and quantum field theory background, the mass gap may be a less familiar concept, but it actually figured in Ruan's lecture this morning, essentially. except it's not usually articulated in this language. One area where the mass gap is important is in topological field theory in 2 dimensions. Actually, Ruan reminded us of more references. Dubrovin and Telemann and Giventhal developed a beautiful theory of topological field theories on the hypothesis that the quantum cohomology ring is semi-simple. Well, that's true when the underlying physical theory has a mass gap. And in fact, if there is a mass gap, there might be several vacua. And in the more interesting case is the case here where there's more than one vacua. The massive vacua correspond to what are called the idempotents of the quantum cohomology ring. When the quantum cohomology ring is semi-simple, it can be diagonalized via idempotents, whose physical meaning is that they correspond to the massive vacua. I only understand the relation here in one direction. If there is a mass gap, then the quantum cohomology is semi-simple, for reasons I can see. But the fact is that in all known examples, there's an if and only if statement. So that would be a nice, all known examples that I can think of anyway. So that would be a nice, even a somewhat heuristic explanation of the only if part of this statement would be interesting. Now, going back to gauge theory, in 4 dimensions, well, the mass gap is a very important bit of physics, as I've told you, but it's also rather surprising theoretically. Or more exactly, it used to be surprising. It's as surprising as something that was discovered 30 years ago can be. By now, we've kind of gotten used to it, although it's still kind of bothersome. So the mass gap comes as a surprise because, well, this is R3, but of course it should now be R4. We're now in 4 dimensions, so I should have written some 4s here instead of some 3s. But in 4 dimensions, the classical action is scale invariant, with g squared now being dimensionless. And since it's dimensionless, you can imagine it being very small. And the classical theory, of course, has no mass gap. Scale invariance guarantees there isn't one. And then if g squared was 10 to the minus 6, you would think that the classical approximation would be good. So it's surprising that quantum mechanically it would turn out that there's a mass gap, even though classically there isn't. Now, first of all, why is it not impossible to have a mass gap? The renormalization procedure that you need to use to define the quantum theory, the word theory is missing here, introduces a mass scale lambda. So even though the classical theory had no mass scale, the quantum theory does. So there's no immediate proof that the theory can't have a mass gap. But the mass gap is very hard to understand because theoretically, based on the renormalization group, it's exponentially small. So in the case I mentioned where g squared is 10 to the minus 6, so why isn't the classical approximation good in telling you that there's no mass gap? Well, the answer is that by some yardsticks it's good. There is a mass gap, but it's e to the minus 10 to the plus 6. So it's very, very little. So this formula certainly shows that there isn't going to be a simple perturbation theory that will enable us to see the mass gap in 4 dimensions. The only hint perturbation theory gives is that perturbation theory doesn't give a clear answer. So even if g squared is 10 to the minus 6, if you look at perturbation theory closely, you find you can't get a clear picture. So you can't use perturbation theory to prove there isn't a mass gap. Perturbation theory gives an expansion like this, where I've taken a gauge invariant local operator of dimension n over 2. So classically, in a scale invariant theory, its 2-point function would be 1 over x minus y to the n. Perturbation theory gives a series in powers of g squared, where the important thing is that well, first of all, the coefficients of g squared are logarithms of x minus y. And of course, the logarithm grows as x minus y goes to either 0 or infinity. So perturbation theory looks dangerous if x goes to either y or infinity. So just with this, only this knowledge, even if g squared is 10 to the minus 6, you'd worry about both ends. But the renormalization group and asymptotic freedom give a similar answer, a simple answer for x minus y going to 0. So that's what the 2004 Nobel Prize for asymptotic freedom was all about. It explained how the strong interactions behave at high energies and short distances. But for x minus y going to infinity, all that the renormalization group and asymptotic freedom tell us is that we're not going to learn much from the fact that the coupling might have been weak. The effective coupling stops being weak. The jargon is that the theory flows to strong coupling, where you can't decide what happens. Certainly you can't decide based on perturbation theory. So that's why we've got both real experiments and computer experiments telling us that four-dimensional gauge theory has a mass gap. And, well, we can say a variety of things about it. The only thing I've told you is that we can't prove there isn't one. The main other thing you can do is to formulate various toy problems that aren't really convincing models of the real thing, but you can hope are good enough models of the real thing, and show that some of those have mass gaps. I won't go in that direction today, though. Now, going from 4 dimensions down to 3 dimensions, at least we don't have classical scale invariants to worry about. We had a parameter with dimensions of mass in the theory to begin with, namely g squared. Remember, classically it had dimensions of inverse length, but when we turn on Planck's constant, it had dimensions of mass. And the renormalization procedure doesn't introduce any other masses. So if there is a mass gap, the mass of the lightest particle is just a number like this root 2 over pi or something times g squared. And since it's just a simple number times g squared, you might have hoped to calculate it by some sort of one-loop computation. But if you think about what one actually can compute in perturbation theory, it becomes clear that this won't work, at least not straightforwardly. So perturbation theory has roughly the same structure we had in 4 dimensions, except that the corrections, instead of being logarithms, are powers. Now, that means that unlike 4 dimensions, we don't have any problem as x minus y goes to 0. When we had a logarithm, there was a problem at both ends, and we needed the renormalization group to straighten it out when x minus y goes to 0. But since a power just vanishes as x minus y goes to 0, in 3 dimensions, just naively thinking of the structure of perturbation theory makes it pretty clear that the classical answer is correct when x goes to y. But if you want to know what happens when x goes to infinity, you just see in perturbation theory that successive terms are bigger and bigger. So you don't really learn anything. So, okay, we can say this, well, I'll mention in a little bit of detail one approach, and then I'll tell you another approach exists. But it's basically an unsolved problem. So, okay. And again, apart from the approaches I'll tell you about, there are all kinds of lattice theories and other things where you can calculate in a truncated version of the problem that you hope might be a good approximation. To tell you a couple of approaches people have tried, though, one involves looking at things from a Hamiltonian point of view. So the Hamiltonian is an operator that acts in a Hilbert space. Sorry, curly A will be something else. That should have been curly H. That formally is defined as follows. You start with the G bundle over R2. So we're doing 3-dimensional gauge theory, but 1 dimension is time. In a Hamiltonian point of view, we get rid of time and just look at space. Space is R2. So we look at a gauge field in R2. Mathematically, that means a connection on a G bundle over R2. We let curly A be the space of connections, and curly G the group of gauge transformations acting on curly A. Then the Hilbert space, again that's supposed to be curly H, is the space of gauge invariant L2 functions on the space of connections. Of course, one of the things that you'd have to do in constructive field theory is to make sense of this formal statement. So I might say in a finite dimensional approximation, there's no problem. You go to lattice gauge theory, then you have a finite dimensional approximation to the space A of connections. And then L2 functions of A, or gauge invariant L2 functions of A, give an approximation to the Hilbert space. But making sense of that in the infinite dimensional limit is a problem. Now our Hamiltonian acting on functions of connections is formally the following operator, where E is called the electric field and B is called the magnetic field. But actually, the integral of the square of the electric field is the Laplacian on the infinite dimensional manifold A, the space of connections. In the second term, B is just the curvature. In a non-relativistic setting, the curvature is usually called the magnetic field, and we write B for it. So what plays the role of the potential energy? This is a gigantic Schrodinger Hamiltonian. There's a potential energy, which is the L2 norm of the curvature. And as I'll explain in a second, the electric field squared is the kinetic energy, the Laplacian. So the statement that the electric field squared is the Laplacian amounts to the following. According to textbooks, the electric field is the canonical momentum to the connection. So if we represent the connection by a multiplication operator, so the physical states are functions of connections, then the electric field is a derivative. And so the integral of of E squared, is the integral of the second derivative with respect to A squared at a point x integrated over x. And hopefully here you see formally the Laplacian acting on the space of connections. So now we've got this operator G squared. It requires a little bit of renormalization, but that actually won't affect what I'm about to tell you. And of course, it has dimensions of energy, but so does G squared. G squared has dimensions of energy. And G squared is the only quantity in the problem with dimensions of energy. So since G squared does have dimensions of energy, the eigenvalues of H, another misprint, the eigenvalues of H in units of G squared are pure numbers like zeta of 2 or 3 to the 1/3 times G squared. So H does require some minor renormalization, but the renormalization introduces no new parameters. And it's true that the eigenvalues of H are pure numbers times G squared. So it's tempting to write H as G squared times H prime, where H prime has eigenvalues that don't depend on G squared. So then H prime looks like this. And its eigenvalues don't depend on G squared. So it's been argued that in some sense we should be able to just drop the second term, take G squared to infinity, and compute the eigenvalues of the first term, which would mean that we would just have to look at the Laplacian on this infinite dimensional space. That's surely too optimistic, but I don't think I can claim to fully understand it. I assume what happens is that although the eigenvalues don't depend on G squared, the eigenfunctions do. And it must be that there's important structure on a length scale of 1 over G squared, and that a lot of the information you need to understand the problem is shrinking out of sight if you try to take G squared to infinity. But that's vague. I don't claim I'm explaining anything. I'm just trying to look at this from the outside and imagine what must happen. Now, my own verdict on this is that understanding the mass gap in either 3 or 4 dimensions is a hard problem, and it'll come as a happy surprise if any kind of reasonable understanding, let alone a proper proof, emerges anytime soon. So therefore, I think the goal of a renewed rigorous study of 3-dimensional Yangmills should be to prove that there is an infinite volume limit by methods that don't depend on knowing whether there's a mass gap. One might describe what one should aim to prove as existence with power law decay. In other words, you won't have, it'll be very, very hard to decide if you have exponentially fast approach to the infinite volume limit. So what one should aim to prove in the medium term would be that you have power law approach to the infinite volume limit. That's even more true in 4 dimensions. I think this is a more realistic goal in 3 dimensions, but certainly in 4. Now, in the spirit of equal time, however, I should point out that there's an ingenious program in 3 dimensions that I don't know too much about and that tends to contradict my philosophy. So there are a lot of papers. I've just given one reference here. So roughly speaking, they try to use this starting point, but not just throw away the second term. They use a lot more tricks I don't have time to tell you about now, but it's important here that we're in 2 dimensions. At least the starting point is that R2 you can think of as the complex plane, and every connection on a bundle over the complex plane defines a holomorphic structure. So they think of the space of connections as being the space of holomorphic structures on what generically is a trivial holomorphic bundle. So what's varying is the Hermitian metric on a trivial holomorphic bundle. And they rewrite the Hamiltonian in that language. And they had a lot of fun and adventures that are hard to summarize. And also, I'm no expert in any case. But, okay. Long and short of it is that they've proposed some kind of expansion which isn't based on any known small parameter. So there's no clear reason that it would work well, but numerically it works pretty well. To me, that's somewhat like the fact that the epsilon expansion for critical phenomena works well in 3 dimensions when epsilon is 1. It's a useful fact. I'm not sure anybody understands well why it's true. It's hard to use it for proofs because of the fact that it's not well understood why it's true, but that doesn't keep it from being useful. My tentative opinion of this program is that, well, it would take a better explanation of why they get good numerical results before it would be useful as input for anything like a rigorous proof. That's a conservative statement. But anyway, if you're going to put a lot of effort into 3D Yangmills, you should form your own opinion of this work. Since I don't know what to say about it, as I've written there. Now, to make it more palatable to believe that one should develop infrared existence theorems, only assuming parallel decay, let's point out that our problem has a natural generalization where this is the right answer. So we just add a sufficient number of fermions with 0 bare mass. By the way, in 4 dimensions, that's a better approximation to the real world than the pure gauge theory is. Because although the up and down quarks are not exactly massless, they're very close to being massless. So a much better approximation in the real world than ignoring the quarks is to treat the quarks as massless. So the real world of strong interactions is actually better approximated by a theory that doesn't have a mass gap, because the pions would be massless, than by the pure gauge theory. Anyway, let's look at this theory in either 3 or 4 dimensions. Here at least I had the foresight to refer to the dimension as n, not 3 or 4. So for dimension 4, the fact that there's no mass gap, if NF is big enough, which means at least 2, was originally proved by 't Hooft. There's actually a corresponding proof by Waffe and me for dimension 3. I'm here, of course, using the term proof loosely. So in renewing constructive field theory, one would hope to find the right framework in which the sort of arguments we gave would turn into real proofs. However, our argument involved ingredients that were general enough that it's plausible that they would become real proofs if there was a proper mathematical theory of this type of quantum field theory. So skipping over 't Hooft's argument, what Waffe and I did, roughly, was to find a correlation function that we could bound below by a positive multiple of what it is in free field theory. We bound it below by saying that if the gauge field A is treated as a classical field, we get a lower bound that's independent of A. And therefore, our lower bound holds after any kind of quantum averaging, as long as the quantum averaging is taken with a positive measure. That last point isn't completely trivial, but it's true here. You need to know that the measure of which you're averaging is positive. So you need to explain a few things about fermion determinants to show that that's true. I won't go into that today, unless people ask afterwards. So, I mean, without explaining technical details, what made it possible to make our argument is that zero modes of the Dirac equation have topological meaning. So even if you have a Dirac operator that doesn't have a zero mode, it has to have low-lying eigenvalues, because under a suitable perturbation, there would be a topological reason that it would have a zero mode. So we had an upper bound on the magnitude of the eigenvalues of the Dirac equation, and that led to a lower bound on certain correlation functions. The lower bound was independent of A, so well, if quantum averaging makes sense, it will survive quantum averaging. So, okay. Well, all I've told you so far is that if we add enough massless fermions, you can actually prove there's no mass gap. But if now I'll tell you something that only works in 3 dimensions, not 4. In 4 dimensions, if there are too many massless fermions, you lose asymptotic freedom, and the theory is believed to not exist. But in 3 dimensions, NF, the number of fermion types, can be as large as you wish. And something very nice happens, which I'm sure constructive field theorists will have fun with one day, which is that if NF is large enough, the dominant Feynman diagrams are extremely simple. So this is meant to be a one-loop diagram with a fermion and external gauge fields shown by wiggly lines. So you have to iterate this one-loop diagram, but you calculate the one-loop diagram and iterate it. And you get a nice story where the important length scale is not g squared, but in effect it's g squared times NF. The difference between them isn't very exciting if NF is 2 or 3, but if we imagine that NF is 10 to the 9, then it's an important factor. And what happens is that at this very big length scale, you get a story which is simple enough that you can understand it from these bubble diagrams. So what you learn by studying the bubble diagrams is that the infrared limit of the theory is a non-trivial conformal field theory in which the dimensions of fields can be computed in an asymptotic expansion in powers of 1 over NF. And this is really an interesting field theory. I'll tell you 1 or 2 facts about it in a second. So I think that if the quest for rigorous understanding will be reinvigorated, this result, for example, will be much more accessible than the proof that the pure gauge theory has a mass gap in 3 or 4 dimensions, just because it's much better understood. I don't know the lower bound. Except, what is this, in any case? That there's a conformal field theory? Well, that's actually something you know better than me, I think. So I'd better not answer. I didn't know that you can prove that there's no mass gap all the way down to -1. 2, I think. For Witten and me, it was, okay, sorry. Maybe that was 1, right. Okay, sorry. Unfortunately, in preparing this lecture, I didn't refresh my memory on exactly how far down you can go with this proof. Maybe it works for 1. Okay, I don't know the answer to your question, though. So this conformal field theory that is believed to be there for sufficiently large NF, although we don't know exactly how large it has to be, is quite interesting. It's not true that the corrections to classical answers are small. The corrections to classical answers can be large. For example, near the ultraviolet, if the gauge group is U1, so that as in the lecture yesterday by Buchholz, there's a 2-form valued quantum field, F mu nu. Near the ultraviolet, F mu nu has dimension 3/2, but the correct value in the infrared is 2. So 2 is a decent distance away from 3/2. That's a pretty large quantum correction. It's not just a measly 1 over NF effect where NF is 1,000,000 to make this a good approximation. So the claimed infrared limit is pretty far from the ultraviolet description, and it's also a pretty interesting type of conformal field theory. So we discussed the problem of the mass gap in pure Yangmills, or unfortunately, we don't have a clear picture. And then we discussed a case where we have a clear picture, but there isn't a mass gap. So now I'm going to talk about a case where we have a clear picture and there is a mass gap. So this comes from the fact that in 3 dimensions, one can add a Chern-Simons term to the Yang-Mills action. So the total action will be the one we've discussed so far, the L2 norm of the curvature. But then we add the integral of the Chern-Simons 3 form. This only works in 3 dimensions, so n is now 3. The integral of the Chern-Simons 3 form with the coefficient k over 4 pi, where the parameter k is an integer for topological reasons. Now, it's much easier to see why there would be a mass gap, because if you just study the classical PDEs that you derive from this Lagrangian, so the I would not be there in Lorentz signature. So in Lorentz signature, you would get a real PDE that you can just solve. And as first pointed out, I think by Desert, Jakeev, and Templeton, when you do that, you discover a mass gap classically. Classically, it's better to call it a length gap, and then you turn on h bar and it becomes a mass gap. So in the classical limit, there's a mass of g squared times k, but it's up to us what k is, and in particular, k can be big. And the classical approximation is expected to be valid if k is large enough. So if k is, well, the traditional problem that we discussed at the beginning was k equals 0. But in general, if k is small, even if it's not 0, then we're going to have trouble deciding what happens. But if k is sufficiently large, there's a good classical approximation demonstrating a mass gap. And then that's a good target to aim for in if a proper mathematical theory is developed. So one would think that in the future, when quantum Yangmill's theory is studied again more intensively, it would be possible to prove that there's a mass gap for all sufficiently large k. Now, okay, of course, technically this is going to be hard. So I wouldn't presume to tell you all the problems you'd run into, but I'll just point out one of them. One snag is that at least some of the cutoffs used in rigorous approaches to Yangmill's theory are hard to reconcile with the delicate Chern-Simons interaction. I find it extremely hard to believe that would turn out to be a showstopper, but it's certainly something that you'd have to grapple with. It's not totally unlike the problems with fermions on a lattice that we're going to hear about tomorrow. So one would think that if people are going to try to study three-dimensional Yangmill's theory rigorously, then while pondering whether there's a mass gap for small k, one could probably prove there is one for large enough k. If you had such a result, what would it be good for apart from giving a fairly interesting quantum field theory model? Well, one answer has to do with topological field theory. I'm going to assume that if it becomes possible to construct this model rigorously in R3, that one will be able to do that on any oriented 3-manifold for any Riemannian metric. M is oriented because we need that to define the Chern-Simons function. But the Chern-Simons function didn't care about the metric. Okay. The reason one expects... Okay. The problem, what is the problem in making quantum field theory rigorous? There's an ultraviolet problem. The ultraviolet problem is actually independent of k. And it's also independent of the metric on the 3-manifold. I know sitting in your armchair, it's easy to make those remarks. But those are things that one would expect to be substantiated in a rigorous theory. And so since the ultraviolet problem doesn't depend on M, and here we're going to have a little fun where we don't even have to solve, well, usually there's a little bit of problem taking the infinite volume limit. But here we're going to work on a compact 3-manifold, so you won't have to do that. However, we will have to know that there's a mass gap for what I'm going to tell you. So although we won't need to know that there's an infinite volume limit, we'll need to know the fact that you would have used in helping to prove that there's an infinite volume limit. So we'll assume that we're on a compact 3-manifold with some oriented, with some Riemannian metric. And now what we're going to do is to scale up the metric of M by a large real number. So I drew 2 manifolds rather than 3 manifolds because they're easier to see. But here's a small 2-manifold, and we scaled it up by multiplying the metric by a constant. But now we want to scale it up by a very, very big factor. We scale it up until any characteristic length scale of M is far bigger than the length scale set by the mass gap. That length scale is 1 over g squared k. So we want the radius of M and the circumference of M and its circumference in any conceivable direction to be much bigger than 1 over g squared k. And you see, by the way, this gets easier for large k because this length scale gets smaller. Now, as I told you before, a quantum field theory with mass gap M is trivial from the customary point of view of physics at distances much bigger than 1 over M. But there's a catch. If you want to be really, really accurate, the statement that the quantum theory is trivial at a distance bigger than 1 over m leaves something out. The triviality means, first of all, that there's no propagating particles that you can produce without a large energy input, and no interesting measurements unless you can resolve very short distances. So if you're like humans on planet Earth, you can only reach a certain energy and you can only get down to a certain length scale, then particles with a mass m that's sufficiently big are out of reach. So by taking our 3 manifold to be very big and assuming we only make measurements on length scales that are characteristic of m, we're putting ourselves in the position of a particle physicist who can't probe what happens at the grand unified scale because sufficient energy isn't available. But it's not true that what survives at long distances is nothing. It's a topological field theory. So instead of just saying that the long distance limit of a massive theory is trivial, a more accurate statement is that the long distance theory of a massive theory, the long distance limit of a massive theory is a topological field theory. The distinction is often not important because in many examples of quantum field theories with a mass gap, the topological field theory you get by going to long distances is trivial. For instance, that's believed to be the case in 4-dimensional gauge theory with SU2 gauge group. I mean, we've discussed a little bit, both Arthur and me, the conjecture that it has a mass gap, but there's a stronger conjecture, which is not only has a mass gap, but the resulting topological field theory at long distances is trivial. You might have trouble finding that stronger statement in the literature, but that should be the conjecture. But that isn't so in the example at our hand right now. If you take 3D Yangmills with a Chern-Simons term, it's not true that the topological field theory at long distances is trivial. What's expected to happen is that the infrared limit is associated to the pure Chern-Simons action. The idea being that the other term in the action, infrared, the other term in the action is an irrelevant perturbation in the technical language of the renormalization group. At short distances, this term dominates, and the ultraviolet problem doesn't depend on k. But at long distances, this term dominates, and you interpret this one as an irrelevant perturbation whose effects vanish exponentially, actually, because there's a mass gap, but exponentially fast as you approach long distances. So technically, the way you say it is that in the infrared, the connection A behaves like a field of dimension 1, so that the Chern-Simons action has dimension 3, which is the right number since we're in 3 dimensions. But by that counting, the Yang-Mills action has dimension 4, which is more than 3, so it's an irrelevant perturbation. So unlike the example with the fermions that is expected to flow in the infrared to an interesting conformal field theory, this theory is believed to flow to the pure Chern-Simons theory. So starting with physical Yang-Mills in the ultraviolet, but with the Chern-Simons term, and flowing to Chern-Simons in the infrared, might be a good route to understand rigorously the 3D gauge theory approach to the Jones polynomial and related knot invariants and 3-manifold invariants. Although I'm not sure, this route might be technically simpler than other options. And it has the advantage that it would be part of a larger program where you would also be understanding models of physical interest that exhibit a range of different types of behavior. The reason I think this might be a good approach, although I should stress that I'm not sure if it would be, is that if you try to think about the pure Chern-Simons theory directly, the action is dimensionless, so it's like a renormalizable field theory, and you look like you have ultraviolet problems on your hand. Now, it's true that locally you can get rid of them in some gauges, but it's hard to use that when you're discussing topological invariants. I really am not sure, but regularization by adding a physical Yang-Mills term might be a good way to deal with the ultraviolet regularization that you need in some form. There's something called a framing anomaly that affects these knot and 3-manifold invariants, which means that a procedure that's too naive can't work. And definitely the regularization that involves a Riemannian metric that you then remove has enough structure to accommodate what the answer is believed to be. Now, I've discussed two modifications of Yang-Mill's theory, one by adding fermions and one with the Chern-Simons coupling. So you can do both at once, and then you get more general conformal field theories. You can also supersymmetrize the whole picture. And there are a lot of fascinating things that are believed to happen. Now, I don't know whether this would be a good approach to the gauge theory description of the knot and three manifold invariants, but certainly a renewed study of quantum field theory that would include different kinds of applications than were emphasized in the past. Applications of interest in geometry would probably bring new ideas to the subject. The same would be true in 3 dimensions. In either 2 or 4 dimensions, if one is to reinvigorate the program of constructive field theory, one should think about applications to other areas of mathematics as well as physics. So in 2 dimensions, there are so many problems one might have talked about that the lecture could have been on 2 dimensions. And if it had been, one of the problems I would have discussed would have been the one we heard from Ruan. And it has the advantage that the necessary constructive field theory methods are much more close at hand. So supersymmetric linear sigma models are obvious candidates that are essentially within reach, one would think, of the type of methods that Arthur told us about. And they're related to many topics studied in different areas of mathematics, not only what Ruan was telling us about. In 4 dimensions, everything is going to be technically much harder, but probably a rigorous study of quantum Yang-Mills on 4 manifolds would have its applications. Thank you.
You left out a discussion of potentially a more simpler potential problem for future constructive field theorists, which would be the Higgs phenomenon for Yang-Mills and 3.
Yes. Well, that's a... Well, that's a valid point. It would have made perfect sense to include scalar fields and discuss the Higgs mechanism. But I picked some problems that were fun, I thought.
Just a curiosity, just to confirm, I mean, 4-dimensional, obviously we're very interested in the Higgs,
Yes.
adding Higgs, but I presume that the problem there would be the lack of asymptotic freedom when you include a Higgs particle, a fundamental Higgs particle.
It's extremely difficult to get an asymptotically free model with scalars. It's not impossible because there are the supersymmetric models, of course. The most obvious Higgs models in 4 dimensions are not asymptotically free and may not exist quantum mechanically, but some will. One might consider picking one of those, using asymptotic freedom to tame the ultraviolet, and enjoying the mass gap in the infrared. You have to make sure that you can find an asymptotically free theory with enough scalars to completely break the gauge symmetry. My guess is you can, but I don't know offhand. Yes?
Do you expect that taking the large and limited dimensional Yangmill theory could be a simplification in understanding the mass gap?
Well, it hasn't yet been a simplification. So I think there's more hope. The question was if I think it'll be easier to understand the mass gap for large n than for SU2. So I think there's more hope, but it certainly hasn't been done. Well, for 25 years after it have suggested the 1/n expansion in gauge theory, there was no real fundamental progress. It's a little unfair. But there was no progress relevant to 4-dimensional models. And then there was, of course, the Modesena insight about gauge gravity duality. And then the 1/n expansion became real in a lot of models. But it's still far from being real in the pure gauge theory. It needs an insight as compelling as that was. And unfortunately, the evidence is that non-supersymmetric Yang-Mills theory, even for large n, isn't integrable.
Well, you know that there are soft ideas on magnetic condensation as an explanation of
Yes.
the mass gap in Yangmills.
Yes.
Do you expect that surface operators that are magnetic defects in pure Yangmills would play a role in understanding the mass gap?
Well, I don't know how to do it, but maybe you or somebody else will do it.
I didn't understand why you said that in the ultraviolet limit the dimension of f is 3 over 2, because clearly if it's a conformal limit, then dimension of f squared should be 3.
No. Sorry. In the ultraviolet, in the theory I was discussing, first of all, okay, let's discuss U1 gauge theory in 3 dimensions, the free theory. The action is f squared. I do not believe the theory is conformally invariant, but in any case, the action being f squared, you can see that although it's not conformally invariant, it's definitely scale invariant. And there's some tricky questions of what's the right statements. I'm trying to avoid them, but I've stumbled already a little bit. But let's try to be naive instead of being rigorous. The action being f squared, if that action is scale invariant, f has dimension 3/2. And
But then you go from f squared to f. That's the
f has dimension 3/2. That was correct. Well, let me tell you something. Take free U1 gauge theory in 3 dimensions. Calculate the 2-point function of f.
Oh, okay.
It's 1 over x cubed. So if you're going to assign a dimension to f, the correct dimension in the ultraviolet is 3/2.
Okay.
Now, there's some subtleties about what's the precise statement, but that last one is a safe statement. However, in the situation I was describing, there is a conformal field theory in the infrared, so that dimensions are more straightforward to discuss. I should say it's believed that there's such a theory, and it's believed that the dimension of f in the infrared is 2. So the situation is believed to be that f flows from an approximate scale invariant theory in the ultraviolet, where the dimension is 3/2, to an infrared theory that's exactly conformally invariant in the infrared with a dimension of 2. So it's not a namby-pamby renormalization group flow where things flow by 1 over n, and you can see it because n is large. The change in dimension is actually from 3/2 to 2.
Isn't the description of this conformal theory?
I believe that, you see, the answer to that question depends on who you are. So if you were a physicist asking, I would have said yes. You calculate everything explicitly in an asymptotic expansion in powers of 1 over n. And a physicist would regard that as a description.
And my question was rather, is there an alternative? Is the description not as a limit of
No, there's no other thing that this is known to be equivalent to. This is not equivalent to anything more elementary. Yes?
In the composition group, when you have cutoffs, you also sometimes like to make slices. So could you use your Chern-Simons regulator, the Yangmill theory, to sort of play also with? It's just like you have 2 cutoffs, but can you slice also in between with the same idea?
By slices, you mean momentum space cutoffs, which you want to change?
No, I mean something that would go with the philosophy of a renormalization group to do things in steps.
Well, sadly, unfortunately, this lecture has been that of an armchair commentator. So to actually do anything is going to be a big program. So you've just asked a question that you can answer far better than I can. So I don't know what would be a good way to. I think it's better to stop there.
You mentioned the Mendocino approach as a possible approach to understand the mass gap.
Maybe we should discuss it. Oh, yes.
But the formula that you wrote for the mass gap, the proportional to the renormalization group invariant scale,
Yes.
shows that you can remove the cutoff and the coupling constant goes to 0. While Maldacena
I think we should discuss it privately. Let's discuss it separately, because too many people are leaving. Well,